Let's calculate the acceleration of an oil bubble in water. Get a container, fill it with water, put in our oil bubble, and let's list the densities of these two substances. Density of liquid water is always approximately 1,000 kilograms per cubic meter. Density of oil varies quite a bit, but 900 kilograms per cubic meter is not a bad value. Before jumping into the calculation, we should probably make sure we actually understand why the oil is accelerating at all, so let's draw in a free body diagram of the oil bubble. So if the dot represents the oil bubble, there are two forces acting on it, the buoyant force pushing it upward, and the force of gravity on the oil itself pushing downward. Because the buoyant force is caused by gravity, you actually always need both of these forces to be acting in a buoyant system. However, we don't immediately know the relative magnitudes of the two forces. Looking at the densities, we would probably figure that the buoyant force is going to be larger in magnitude since the oil is less dense than the water, and indeed that'll come out of our calculation once we write out the forms of the forces. So let's do that. With this free body diagram, the net force must be the buoyant force plus the force of gravity. Now we know that if we make the buoyant force positive, the force of gravity is going to have to be negative. Looking at our lecture notes, the buoyant force is equal to the density of water, not oil, but water, times little g times the volume of the bubble. The force of gravity is negative, as we said, the density of oil times little g times the volume of the bubble. Basically, that last term is just m times g, because the density of oil times the volume of the bubble is the mass of oil. But we also know that, according to Newton's second law, F net equals ma, so if that's true, we can write out that since the mass of oil is the density of oil times the volume of the bubble, F net equals rho sub O times VB times A. Well, that means that this term here must equal the sum of these two terms up there, so let's equate them formally. And if we do that, now we're actually in a position where we could solve for the acceleration in terms of the other quantities that we know. If we divide through by the density of oil times the volume of the bubble, we get an expression for the acceleration, and we can simplify this a little bit by pulling out a factor of g. So the acceleration is equal to little g times the ratio of the water density to the oil density minus 1, that entire quantity. Two interesting things to note about this. One is that the expression for the acceleration does not depend upon the volume of the bubble at all. That cancels out completely. The other interesting thing is that if you look, the density ratio obviously matters a lot. If you have two substances that are approximately the same density, rho W over rho O will be approximately 1, and that means that the acceleration is approximately 0. Well, that's not surprising. Something is referred to as being buoyantly neutral if it feels no net force, meaning no acceleration. Now, if you have a huge contrast, either a density ratio that is much bigger than 1, or a density ratio that is much less than 1, then the magnitude of the acceleration will be really big. It'll still be proportional to little g, after all of this stuff is assumed to happen on Earth, but the density ratio obviously makes a huge difference, so if you instead had an air bubble in water, it would experience a much larger acceleration than our oil bubble does in water. To finish off the problem, let's put in some values, and all we need to do is multiply this out to find that the acceleration of the oil bubble in water is 1.09 meters per second squared. So an appreciable acceleration, but one that is smaller in magnitude than 9.8 meters per second squared. Also, the fact that this acceleration is positive, and that in our free body diagram we had assumed the positive direction was up, tells us that indeed oil does rise in water.